All right, let's get started with today's material. I don't know. We won't worry about it. All right. So our transition now today is talking about analytic geometry. Today is just meant to be an introductory, just give you a taste of analytic geometry. We're not going to delve into it very far. Intuitively, what is analytic geometry? Basically taking geometry and adding a coordinate system to it. And so when you add a coordinate system to geometry, the amazing thing that happens is we're now able to express a bunch of geometric figures with equations. And we're able to start using equations to describe and prove things. And it's absurdly useful. The person most credited with the discovery of analytic geometry is René Descartes. You may have heard that name before, René Descartes. The story goes that he had very poor health, had to spend a lot of his time in bed, and didn't have as much time as he wanted to work on mathematics. And so he felt that the way of doing these Euclidean proofs, doing our proofs in geometry the way that we've had to do proofs thus far, he felt like it was a bit tedious. You always had to come up with this clever trick for proving this problem, and then a clever trick for proving the next problem. And it felt like the trick for proving one problem doesn't necessarily roll over to another problem or to another problem. And so he came up with this new way of doing geometry, where when we can start describing things with equations and coordinates, it's going to turn out that the stuff rolls over real nicely. I told you a bunch of the stuff that we did, for example, already in three-dimensional geometry. The reason we barely touched that is because nobody messes with 3 dimensions anymore without using analytic geometry and describing planes with equations now and describing lines with equations. So that's ultimately what this is going to lead up to, is we're going to be able to start describing these geometric figures with equations. So how do we start out? We start by coordinatizing a line. So how does this work? You start out with some arbitrary line L. There it is. And you pick some unit, because we're going to measure on this thing. Okay. So we're going to pick some arbitrary unit. There's our unit. That's 1. Good? Yeah. Now we pick some point on our line, doesn't matter where, and we label that point O. We call that the origin of our line. We then go and we take this distance and we go out there and we make a tick mark. And we're going to call that 1. Right. And we're going to go out, we're going to make another tick mark, we're going to call that 2. We're going to call that 3. We're going to call that 4, etc. Well, we're really just marking these every unit. We call that 1, 2, 3. We pick one side arbitrarily that we're going to call the positive side, and we pick the other side and we arbitrarily call it the negative side.
You can switch it easy, right?
Huh?
That's what we're saying, arbitrarily switch it.
Yeah. So this is one way we could have coordinatized this line, putting -3 there, -4 there. I could have just as easily called these a positive side, this a negative side. Right. And I didn't need to draw my line this way. There's nothing wrong with coordinatizing the line like this. I could have picked this as my origin, start doing this, called this my positive direction, that's 1, that's 2, that's 3, that's 4, and I could have called this a negative direction. Completely arbitrary. Right. So that's coordinatizing a line. Now, we can start talking about the coordinate of a point on the line. The coordinate, so let's not mix up the numbers and the points. The numbers here were meant to be the coordinates. Probably should have held off on that for a second. What do? We pick some point on the line. Pick a point, any point on the line. That's the point piece of x. Okay? We call the coordinate of the point the length to that point from the origin. Okay. So if this is piece of x, is x. So piece of 1 would be the point whose coordinate is 1. Don't mix up the points and the numbers. Right. If this right here is piece of x, this distance from 0 to here is x. And so that has a coordinate x. And so we're assigning a number to every point. Right. And so we're using the completeness axiom here. We said that to every point on the line, there's a corresponding distance that gets you to that point. There's a corresponding length that gives you that number as its length. Right. There's a corresponding segment that gives you that number as its length. That's how I should have said that. So we're guaranteed, pick any x you want, pick any point p of x you want. This is in some segment. We are guaranteed by the completeness axiom that that segment has a length that's a real number. We call that length the coordinate of that point, which we call x. Now, as a matter of convention, we pick one side, we label those coordinates positively. We do the same thing on the other side, but we just label them negatively.
Right.
Now let's talk about finding distances between points really quick on the line. So I've got some line here. What is the distance from some number A to B? Let's pick concrete numbers for a second. How do I calculate the distance from negative 2 to 3? What's the distance from negative 2 to 3?
5.
5. How did you get that?
I added the absolute value of each together.
Okay, that's one way to think about it. But
The distance.
let's try this one. What's the
I added
distance
the distance
between
from
3 and 1?
2.
2. How'd you get that?
Subtract 3 from 1.
You did 3 minus 1. Notice the same thing works when you're calculating the distance from negative 2 to 3. You do 3 minus negative 2.
Right.
Same concept.
Right.
Now, what would have happened if you accidentally did 1 minus 3 instead? What would you have gotten?
Negative 2.
Negative 2.
You would have gotten negative 2, which is the negative of the answer you wanted. What would have happened if you accidentally did negative 2 minus 3?
You would have got negative.
You would have got negative 5, the negative of the answer that you wanted.
Right.
And so the distance, we define the distance here to be x1 minus x2 absolute value. That gives you the distance between any 2 points on the line.
Period. Because x1 can be negative or positive.
Yeah.
Because-
So
because
the
it's,
result of this subtraction might be negative or positive, we don't know. It depends on which one's the bigger number, which one's further to the right.
Right.
If x1 is 3 and x2 is negative 2, then this difference gives you a negative number.
You don't listen. Listen.
Oh, did I say that backwards?
Yeah.
That's because I wrote this backwards. Usually you write x2 minus x1.
Okay.
But thank you. You're on point. You're understanding what I'm saying.
Yeah.
So that distance, or when you calculate that difference, it's going to give you the same number, but either positive or negative, depending on which one's further that way. Since we don't want to have to keep track of which one's which, you just take the absolute value. Gives you the distance between the points.
Right.
Good?
Yeah.
All right. So that's coordinatizing a line, and that's calculating distances on a line. Now, let's upgrade. We want to coordinatize the plane. How do you coordinatize the plane? So you start out with 2 lines that intersect at a right angle, 2 perpendicular lines.
Right.
Doesn't matter how you draw them.
It's your origin.
Here's one, here's the other. Where they intersect, you call their origin. You pick some unit. And then you coordinatize both lines with that unit.
Right.
And so then we go on coordinatizing this line with that unit, and this line with that unit. And in coordinatizing it, we have to call one side of this line positive, one negative, one side of this line positive, one negative.
Right.
So I can call this the positive for this one, and I can call this way the positive direction for this one. Completely arbitrary how you set this coordinate system.
Right.
There's a lot of choice in it. I don't know, none of you guys have done physics, have you?
No.
In physics, the first thing you do is you set up your coordinate system to represent your physical problem. And since how you set up the coordinate system is somewhat arbitrary, there's a lot of cleverness you can be really clever in solving a physics problem by choosing a good coordinate system to represent your problem.
Right.
So a lot of choice in it. As a matter of convention, we choose to write the lines, we choose to draw it like this, which you're very familiar with.
Yes.
Draw it so that this line is straight up and that line is perfectly horizontal. We coordinatize it. And as a matter of convention, we decide to call the right-hand direction the positive, the left-hand direction the negative, the up direction positive, and the down direction negative. Nothing sacred about that, just a matter of convention. Completely arbitrary. Let me kind of follow along in the book to make sure I'm also not skipping over anything. So let's see. Coordinatizing the line, we did that. Probably should have read some of the definitions. So when I coordinatize the line before that we just erased, this is definition 15.1. The author says, we will refer to the above construction of coordinates as a coordination of the line with point O as origin of the coordinates. So definition 15.1, that's talking about when we coordinatize just a one-dimensional line. Now we get to definition 15.2, which is coordinatizing the plane. So what does the author say to do this? He says, choose point O in the plane. So we choose our O. What's next? We call this point the origin of the coordinates. Choose any two perpendicular lines through O. There they are. Call these lines coordinate axes. Coordinatize each of the axes with the point O as the origin of the coordinates. Select one of these lines and call it the axis of abscisses. Select the other one and we're going to call it the axis of ordinates. Okay, let's make sense of that really quick. So to distinguish between these two coordinatized lines, we need to name them. You with me? So we call one of these lines the abscisses, and we call another one the ordinates. When we draw like this, as a matter of convention, we choose to call this axis the axis of abscisses, and we choose to call this axis the axis of ordinates.
Ordinates and abscisses?
Uh-huh.
Spell it.
Yes. Let's make, well. Let me see if there's two S's in abscisses. Absciss, yeah, there is. Abscisses, and then ordinates. So abscisses and ordinates. Now, this language is kind of dying out. You don't really come across abscisses and ordinates except for in older textbooks or more advanced textbooks. Typically, the axis of abscisses we just call the x-axis. And the axis of ordinates we just call the y-axis.
Ordinates. Okay,
Yes.
Ordinates.
So if you have some, well, we haven't talked about a point yet, but so your x-coordinate is often called an abscissa, and your y-coordinate is often called an ordinate, using the language that you're used to.
Well, right now we use x-axis and y-axis.
They're saying the same thing.
Well, yeah.
I'm just telling you that this language, abscissa and ordinate, it's dying out, so it's less common, but it pops its head up again in more advanced textbooks. It also pops up its head in older textbooks.
Right.
This is just familiarizing you with the language. So if you're reading a textbook and it's talking about the abscissa, it's talking about the x-coordinate. And if it's talking about the axis of abscissas, it's talking about the x-axis. So this is simply to get you comfortable with
So the
terminology.
x-coordinate would be, right, let's just say, it'd be the first coordinate. So they would refer to the x-coordinate as an abscissa.
Yes.
Interesting.
All right. So ordinates, I think we're, let's see, theorem one. The coordinate axes separate the plane. All right, so let's talk about that before we talk about the actual points. Now, so we set up our coordinate axes, right?
Right.
Now, notice that they split the plane into 4 pieces.
Yep.
Now, the first theorem that the author does in the book is he proves that if 2 points are not in the same quadrant,
Right.
then there's a segment between them intersects
At least
one of the axes, at least one of the axes,
Right.
maybe both.
52.
And if they're both in the same, then the segment between them does not intersect one of the axes.
Right.
Now we've already done this proof. The way that we did the proof is if you have an angle, if you have 2 points in the interior of the angle, then
The points in
the segment between them does not intersect either of the angles.
Right.
If you have a point inside the angle and a point exterior to the angle, then the point intersect the angle at least 1 point.
Right.
So we've already proved that. Just give you the idea for the proof. How do I know that if my picture looks like this, these 2 points, how do I know that the segment connecting those 2 points intersects one of these axes?
Because they're on opposite sides of the line.
They're on opposite sides of the y-axis.
By definition.
And so by definition, they have to.
Right.
By here, they have to intersect both.
Right, because they're on opposite sides of each line.
Perfect. Here, they have to intersect
At least one.
at least one. Here, they can't intersect either. Because if they did intersect one, they'd have to be on opposite sides. But they're on, perfect, you got the logic. Okay. So that's the first little theorem that he does. Not a very difficult one. Now, since we're broken up into these 4 quadrants, we named this quadrant the first quadrant, We name this quadrant the second quadrant. We name this one the third quadrant. And we name this one the fourth quadrant. When you decide to coordinatize this way, again, completely arbitrary, just a matter of convention.
Of which quadrants?
Yeah, so if I say, let's look in the third quadrant, it is universally understood that I'm talking about down here.
Right.
Yeah.
But if you label it different.
Yeah.
Right, so there's no reason that this labeling is special. It has nothing to do with, in no way more natural than some other labeling. It's just the labeling we've all chosen to go by, so that we can name these things.
Right.
So it's just a labeling for convenience of communication.
So if you want to, you can read it.
All right, now let's talk about the coordinates of a point. We know how to find the coordinate of a point on a line, right? Let's go back to that picture. When we coordinatize a line, how do I find the coordinates of this point, p sub x?
Calculated the distance between.
It's the length of this segment.
Right, it's the length of the origin and to the point.
Perfect. Now, how am I going to coordinatize a point out here?
You're going to give it a coordinate on the x-axis and a coordinate on the y-axis.
Be very, what do you mean? How do I get this thing, its coordinate on the x-axis? It's correct here. What do you mean? Try and be a bit precise.
Okay, you drop an altitude down.
Drop an altitude down. Okay, so I'm going to do exactly what you're saying. I'm going to construct a line parallel to my y-axis through that point.
Right.
Let me call this L1.
And then another one that's parallel to your x-axis.
So there's L1, and I'm going to construct another one parallel to my x-axis. This is L2.
Right.
Now, this point right here, let's do black for my points. This point right here intersects my axis somewhere. At some point, we're going to call it p sub x.
Right.
And this intersects my y-axis. At some point, I'm going to call it p sub y.
Right. Coordinates to that are x, comma, y.
The coordinate, we know the coordinate for this point on this line
Right.
is just x. And we know the coordinate for this point on this line is y. So we're going to say at this point, P has coordinates x, comma, y. And so we refer to x as its x coordinate, or its abscissa. And we refer to y as its y coordinate, or its ordinate. Again, there's nothing special about these letters x and y. It's just as a matter of convention, we choose to use them.
Right. Is there a certain reason we chose to do x first? Chose to do the ordinate, the abscissa. The abscissus.
So when you look at the language, abscissa, I can't remember the etymology on it, but it somehow ties into the first one. So when you're coordinatizing, you have your first one, and then you have your ordinate.
Right.
And so we tie the x with the abscissa, probably just because of alphabetical order. Now, René Descartes was the first one to start using letters at the start of the alphabet, A, B, C, for constants, and then letters at the end of the alphabet, X, Y, Z, for variables. So he's the first one to make this a standard practice, and so it's largely because of him that we're associating the X, when you're talking about some arbitrary point, the X for the X coordinate, the Y for the Y coordinate, largely just come from him. So a lot of the time, whoever are the first people doing this, whatever notations and habits they pick up kind of becomes a standard for other people getting into the field.
Right.
So a lot of it's just an accident of it's the way that he chose to do things, and so now that's the way we do things. Anyways, so now we know how to assign a coordinate, a pair of coordinates to every point in the plane. Pick any point you want in the plane, construct the two parallel lines to it.
And there is.
The line parallel to the y-axis has to intersect this line.
Right.
Yeah.
How do I know that this line has to intersect this line?
Because it's parallel with the y-axis, and the y-axis intersects the axis.
What was your question?
You've got the intuition for it. I'm saying, how do I know that L1 intersects the x-axis?
Just point PS.
Other than saying, well, duh, look at the picture.
It's perpendicular to a It's perpendicular to the y-axis, which intersects the
It's
x-axis.
parallel to the y-axis.
That's what I'm saying.
Which is
Parallel to the
and
y-axis.
perpendicular to the
Perpendicular
axis.
intersects the,
Right, so it has to be perpendicular to this one.
right.
So two slightly more rigorous ways we can say that is, if L1 didn't intersect this, L1 would have to be parallel to this. But then L1 would be parallel to this, and L1 would be parallel to this.
Contradiction.
And so these two lines would have to be parallel to each other. But we know that they intersect.
Which is then it's
So that would be a quick way to prove it. And similar thinking for that line. So they have to intersect them at some point. With the exception of when it actually lies on the line.
Right,
Then it intersects it at every point. So what do we do in that case?
the
Imagine that this was L1.
zero.
Can I be excused for a couple minutes?
Sure. Imagine that that was my L1. We're talking about this point right here now.
yeah. Where
It's,
L1 and L2.
So where this line drops down,
it's gonna be x comma 0.
notice that
No, it's not, it's gonna be y comma.
it didn't change anything.
Oh, it's gonna be 0,
L1 still intersects this line at a single point,
Right,
even though it's completely hidden this. And this line still intersects this line at a single point. So it didn't change anything to have one of these lines coincide with the other. We still coordinatize the same.
it just changes
The only way that you get to actually lie on it is if you choose the origin. And so we can say we give the origin coordinate 0, 0. And then go from there. Every other point, you can coordinatize this exact way.
right.
Make sense?
Yes.
Okay, so that's how we talk about coordinatizing the plane, giving coordinates to every point. Now, I'm overstressing this, but I want you to understand how crucial it is what we're doing here. We are now assigning numbers to geometric objects over and over again. Every point now on the plane, I have now assigned a set of 2 numbers to.
Yes.
You're so comfortable with this, it's hard to appreciate what a leap this is. We used to have some point, and now we're coming over here and we're saying, and we're calling that point 3.15 and 7.
Right.
It's a little bit strange what we're doing. Assigning numbers to these geometric objects. Assigning points to these, assigning sets of numbers to these points. Why on earth would that be useful? Seems so arbitrary. Now we'll see why it's so useful.
Doesn't every point in space have a coordinate?
See, you're so used to thinking about that you're so used to connecting the algebra and the geometry together. That's what we do in analytic geometry. It's kind of combining those two together. But this whole thought of even assigning numbers to points was such a big leap. Why would you assign coordinates to points? A point is that's a point. What on earth does this have to do with this? And you might say, well, it's the distance down and over from this other point. Okay, fine. Why is that useful?
Tells location.
Location relative to another point. Where's that point?
It's the one that makes everything up.
Yeah, so it's still completely relative. Position's relative. You always have to talk about position relative to some other point. So you say, yeah, it gives me the position relative to some other point. I can just say that point's where that point is. Instead of saying it's this far from some other point that you then have to say, here's where I'm going to start measuring from.
Right.
Trying to give you a sense for why this was such a leap. Trying to give you almost a sense for it shouldn't be that intuitive that you can just assign numbers to these points and have it magically be useful. Which is going to turn out to be the case. It's insanely useful.
You can just assign numbers to it, and it's
Yeah, this
So,
coordination turns out to be extremely useful, and we're going to see some of that in action.
is what you're saying is knowing the coordinates and the abscess of these points help find measurement?
They help us describe and construct geometric proofs. So I told you it's ridiculous to even try and do 3-dimensional geometry without analytic geometry, without these equations to describe our geometric objects.
Right.
The big value that this is going to give us is we're going to be able to start describing geometric objects with simple equations, which there is no reason to expect that that would be the case. You're so used to thinking about y equals 3x plus 2 as a line, but why are you comfortable thinking about that as a line? That is just some equation, some relationship between x's and y's. What does that have to do with a line? That was a big breakthrough. That you could describe geometric objects, infinite sets of points, with equations. So let's go on and start talking about our first equations of lines then. We'll do it over here. So we start out with coordinatizing the plane. Here's our coordinates. Here's our origin O. Okay. Now let's think about a line parallel to the y-axis.
Okay.
What do I know about this line over here, L1?
It's perpendicular
It's
to
perpendicular to the x-axis.
the ordinate.
So-
abscissa.
It's perpendicular to this, which means it has to intersect it somewhere.
Right.
Let's say that it intersects it at some point. What should we call it? Some point A. Well, we'll say some point P with the coordinate x. Okay? So what do I know about all the points on this line, L1?
They also have a line. There's a line between the point on.
Pick some random point on here. What do I know about this point?
It's on a line perpendicular to the.
It has a coordinate off point X.
It has a coordinate. It has an x coordinate. What is that x coordinate going to be?
X.
It's going to be that little x there.
Right.
So this thing's x coordinate is going to be little x. I don't know what its y coordinate is going to be, but its x coordinate is going to be little x. What about this point?
Also the X.
Its x coordinate is also going to be little x.
Right.
What about this one?
Yes.
This one? This one? All these points have the property that their x coordinate is going to be little x. Let's pretend that this was now little a. Sorry, I should have done that before. So little a here, little a here, little a here. All these have their x coordinate little a, right?
Right.
And so we can describe this whole line. What line is that? That is a line where all its x coordinates equals little a.
Yeah.
Or to get more concretely, if I say let's look at the line x equals 2, what does that mean? That means we're looking at the line that intersects the x-axis at the point 2.
Right.
It's all the points that have as their left-hand element 2. That have as their x-axis 2.
Right.
Similarly, let's look at some other line, L2 here. And it's going to intersect this point, intersect the y-axis at the point P sub B, where B is the coordinate on this line.
Right.
What is the property that all these points have?
B. They're all their points B.
All their y coordinates are B. All their ordinates are B. This one has all its abscissas A. This one has all of its ordinates B. Or in other words, this is a line y equals B.
Right.
Okay, yeah.
You see it? And so if I asked you to plot the line y equals 1, well, we'll say negative 1, that is going to be this line right here, where it crosses this x, or the y-axis at negative 1.
Right.
Make sense?
Yes.
Okay. So that gives us our lines parallel to the y-axis and our lines parallel to the x-axis, and ways to describe them with equations. Now what we're going to move to is, he gives an example first, and then we do the proof. You've seen these examples a lot, but we'll do it anyways. So now, let's look at just an equation for a second. And ask ourselves a question. Let's look at the equation. I'm not sure which one he used. Doesn't really matter. We'll make them up. Let's look at 2y plus 4x, I don't know, plus 6 equals 0.
Okay.
Here's some random equation. The question is that equation somehow encompassed by a line? Let's just do an analysis for a second about all the x's and y's that happen to satisfy this equation.
Okay.
So let's think about those for a second. And let's plot those points. So what are some x's and y that make this equation true? First off, if x is 1, what does y have to be to make the equation true?
8.
What?
Yeah, 8. Is that wrong?
If x is 1, what does y have to be to make the equation true?
Oh, sorry. I was not thinking about that.
Let's really quick solve this equation for y, and then that will help us.
So you're saying x equals 1.
So this is me really quick solving for y. Y is equal to negative 2
Y is
x
equal to-
minus 3. Okay.
That's what I was.
How'd you get that?
I move that to the other side, that to the other side, divide everything by 2.
Okay.
Okay. So we're looking for all the x and y's that satisfy this thing.
Right.
Notice that when x is 1, what is y?
When x is 1, y is negative 2 minus 3.
So what is it?
Negative 3.
It's
Negative
negative
3.
5.
Negative 5.
How are you getting that stuff?
Plug in 1 for x. What's negative 2 minus 3?
5. Okay, yeah,
So if x is 1, then y is negative 5. 1, 2, 3, 4, 5. That's a point somewhere right here.
So, is what you're saying, all of this depends on
What?
x's factor?
Here's what we're going to do. This is just experimentation. We are simply going to look at all the x's and y's that satisfy this thing, and we're going to just plot those points.
Okay.
So we're going to take all the x's and y's that satisfy these things, interpret that as a coordinate, and plot that coordinate somewhere on here. Alright, so what about when x is 0? If I plug in 0 for x, what does y have to be?
Negative 3.
Negative 3. If I plug in negative 1 for x, what does y have to be?
Negative 1 for x.
It's
I thought you were
1.
saying-
It's 1. Positive 1.
What's negative 2 times negative 1?
Or it's negative 1.
Negative 1. And what happens when I plug in negative 2 for x?
Positive.
Positive 1.
Yeah.
What happens when I plug in negative 3 for x?
Negative 2.
Positive 3. And we notice that if we keep plotting all these lines, or all these points,
Why don't you just use the rise and run formula?
we haven't derived that formula yet. How do you know that formula works? So far what we're doing is we are just noticing that if I plot, I look at all the x and y's that satisfy this equation, I interpret them as coordinates,
Right.
and I start plotting them, it seems like a line comes into existence.
It does. Okay.
That's what it seems like.
Right.
So here's what our next theorem is going to be. It is going to be that case. It is going to be that if you take any equation of the form, ax plus by plus c equal to 0, where a, b, and c here are just constants, pick any three numbers a, b, and c you want and express it this way. We are going to prove that this describes a line.
Okay.
So I'm going to go two directions. I'm going to show that all the points that satisfy this equation give us a line, and then I'm going to say, now pick any line you want, and there is a corresponding equation like this describing that line. And so we're establishing a one-to-one relationship between these types of equations and lines. And once we do that, we can start talking about these equations as though they are the line,
Right.
or the line as though it is that equation.
Right.
So that is what we're out to do from here on out. And in this, we'll get our equations you know and love. So we're going the first direction here. I need to show that pick any equation like this you want. I need to demonstrate to you that that in fact describes
A line.
a line. You with me?
Yeah.
Okay, we've got a couple cases here. So, first off, notice that A and B can't both be 0. Otherwise, this is nonsense.
Right, then it's C.
Because then I get 7 equals 0, which is nonsense.
Right.
Well, C.
The only way.
Well, what
So-
if all three of them are 0?
Okay, all three of them can be 0. That's fine.
One can be 0.
But here's what I'm going to say. I'm going to say, under the condition, pick any three numbers, A, B, and C you want, where both A and B aren't 0. At least one of them is not 0.
Right.
Okay.
Then, you are given, then there's a corresponding line that that equation captures. Then all the points that satisfy that equation are a line.
Right.
That's what I'm going to argue.
Yeah, okay.
So if we have this where we don't have A equal to 0, where A is not equal to 0 or B is not equal to 0. One of them has to be a non-zero value. All right, case 1. Let's handle the case where a is equal to 0. If a is equal to 0, what do we get? I get b times y plus c equals 0.
Right.
Move the c to the other side. I get b times y is equal to negative c. Divide both sides by b, and I get y is equal to negative c over b. You see that?
Yeah.
Now we already know that's a line. We've already talked about these special cases. That is a line. What kind of line is that? That is a line parallel to the x-axis that goes through the y-axis at the point negative c over b, whatever that number is.
Right.
Yeah, okay, yeah.
Perfect. Next case. Handle the case where b is equal to 0. Well, then what do we get? So if b is equal to 0, this is 0. Move the c to the other side, makes it negative. Divide both sides by a. And you're left with x is equal to negative c over a. And now,
Also a line.
that is also a line parallel to the y-axis that goes through the x-axis at the point minus c over a, whatever that number is.
Right.
Okay, so we've handled 2 special cases. Now let's handle the case where both a and b aren't 0. Go ahead.
If the A correlates with the x-axis, y did.
No, A, B, and C here are any numbers. Here's what I'm saying. Give me a number.
5,
5. Give me another number.
4,
2,
Give me another number.
9.
This is a line. And now you can give me new numbers, and I'm going to show that that's also a line. And you can give me new numbers, I'm going to show that's also a line. As long as you give me 3 numbers, where these 2 numbers are not both 0, it will always give me a line.
I'm wondering, when it says a equals 0 and then it goes to y equals,
So,
Negative c over b, and then when it's b equals 0, it's x equals c a. Why is that? Why?
okay, let's write out one of these cases a little bit better. I think this is the case where I lost you, so let's do this one.
Okay.
So, I don't know what you chose for x, or for a.
Okay.
But you told me you chose 0 for b. So I get plus 0 times y plus c is equal to 0. Here's what I know. I'm trying to prove to you that this is a line. We got it, everyone. I'm trying to prove to you that this is a line. What's 0 times anything?
0.
0. That term goes out. So I'm left with ax plus c is equal to 0. Is this a line? My whole argument is this is a line. Move the c to the other side. I get ax is equal to negative c. Divide both sides by a. I get x is equal to negative c over a. Is this a line? Yes, this is one of the special cases we talked about earlier. X equals a number is a line parallel to the y-axis that crosses the x-axis at the coordinate little a. So this is a line parallel to the y-axis that crosses the x-axis at negative c over a, whatever you chose for c and a.
Okay.
And it will always be that case.
I
Good?
understand you now.
Perfect. So now we got to handle the case where both a and b aren't 0.
Right.
Yeah.
And this is the most interesting of the cases.
If
Okay.
they're not, or if they were, they can't be, right?
So when you gave me 3 numbers, it could have been 1 to 3 possible cases. Because you had to give me 3 numbers, A, B, and C, where at least A was not 0 or B was not 0. I'm handling all possible cases. I handled the case where A could have been 0. I say, then here's the line. Whatever your C and B are, here's the line.
Okay.
You could have given me B as 0. In that case, here's your line. Now I'm going to handle the case where both A and B aren't 0, and I'm going to show you the line that you just described.
If it was a equals 0, then it wouldn't come out to that equation equaling 0, right?
So when you pick A equal to 0, that's this top case. If A is 0, then I'm left with by plus C equals 0.
Which wouldn't equal 0, correct? That's not true, right? Or it can.
There's y's that make this true. Look, let's do concrete case. Again, you're going to give me 3 numbers. This time, we're going to say the first number you give me is 0.
Okay.
So you give me 0, x, now give me another number.
5,
5, y, now give me another number,
3.
is equal to 0. I'm telling you that this is a line. What line is this? 0 times x, that's just 0, so get rid of that. Subtract, so we get 5 over y is equal to negative 3. Divide both sides by 5. We get y is equal to negative 3/5. What line is this? This is a line that has all its y coordinates negative 3/5. That is a line right here. This right here is the line y equals -3/5.
Okay.
You just described to me that line. So I need to show that for any numbers you choose, if we were to plot all the points that satisfy that equation, the consequence would be a line. The result would be a line.
Okay. Then, so you're trying to prove A does not equal 0 or B does not equal 0?
No. I'm telling you, here's the condition. You give me any three numbers, A, B, and C. The only rule is either A is not 0 or B is not 0. That's the only restriction I put on you.
So one of them can.
One of them has to be a non-zero number.
Okay.
At least one of them. They can both be non-zero numbers, but at least one of them is a non-zero number. If you give me three numbers, A, B, and C's, and you make sure that you don't give me both those zeros, I'm telling you, you just described a line. That's why I proved it to you.
Okay. Yeah.
So no matter what numbers you chose for those, you're always giving me a line. So if you happen to pick A equal to 0, I showed you how you gave me a line. If you happen to pick B equal to 0, I showed you how you gave me a line. Now we need to handle the case where A is not equal to 0 and B is not equal to 0. Right?
Yeah.
And I need to prove to you that this still gives me a line.
Right.
You with me?
Yes.
So I need to show that all the x's and y's that satisfy this equation end up giving me a line. All right, how am I going to do that?
You gotta go through all the different cases. You've already done.
So first off, I'm going to point out to you that to notice that an x and a y that satisfy this equation are when x is 0, y negative c over b.
And when x is 0.
Notice that if you plug in this for x and you plug in this for y, you get a true equation.
Very good.
Well, one of those.
This is
0.
a point that satisfies this equation.
No, because one of those is 0, right?
No, this is why I'm plugging in for my x and my y now. Let me plug these in. What are we saying? I'm saying that pick all the coordinates x and y that satisfy this equation. Pick all those coordinates. Pick all the pairs of numbers x and y that satisfy this equation. Then when we plot all those coordinates, it's going to give us a line. That's what I'm trying to show you. So here is one set of coordinates that satisfy this equation. Because notice that a times 0 plus b times negative c over b plus c, what does that equal? So I plugged in 0 for my x, and I plugged in negative b over c for my y. You with me so far?
Yeah.
Okay. What's a times 0?
0.
0, so ignore that. Notice that the b cancels out with the b in the denominator, and we're left with minus c. What's minus c plus c?
0.
0. It worked. It satisfied the equation. Here is a point that satisfies that equation. So, I'm not sure what exactly this point looks like when we plot it. So, pictures lie. Don't read too much into my picture here. But the point is, this satisfies it. I'm going to plot that point right here. Here's my point, 0, negative c over b. Remember, c could have been a negative number, so that could be positive.
Yeah.
Okay, so I got this point satisfies this equation.
What if x wasn't 0? Or does
Doesn't
x
matter.
have to be 0?
I am saying all the points that satisfy this equation result in a line. Here's one point that satisfies that equation.
Right.
Okay, yeah.
Okay, I'm going to give you another point that satisfies the equation. Here's another point that satisfies the equation. When our x is
CA.
negative c over a,
C over A.
and our y is 0. Here's another point that satisfies that equation. You plug those values in, and you're going to get it equals 0.
Yeah.
Okay, so let's plot that point. I don't know where that point would be, but I'm going to pretend it's right here. Pictures lie. You with me?
Yeah.
Okay, now I have 2 points plotted. In geometry, 2 points give me a line. So I know at these 2 points, I can set up a line through these 2 points. Hopefully I draw this somewhat decent. So there's the line. What I am trying to argue is that all the points that satisfy this equation fall on the same line. Here's 2 points that satisfy the equation. Here's the line that they fall on. Now I need to show pick.
Points satisfy that equation.
Exactly. Now I need to show pick any other point you want. It also falls, or it also satisfies that equation.
Right.
Sorry. Other way. I need to show pick any other point that satisfies this equation that you want, and it's also on that line.
Right.
So now we start out with x and y. Let's say that x and y
Tony?
satisfy the equation. Go ahead.
By satisfies the equation, it, ax plus b equals y plus, not equals y, by plus c equals 0. So whatever you plug in, it has to equal 0. Is that
Yes.
what it means by satisfies
Exactly.
the equation?
Exactly. So x and y are going to be any two values of x and y you can plug in here that make this equation true. That make the left-hand side evaluate it to 0.
Okay.
Same thing. Perfect. So now I pick some other set of coordinates, x and y, and I got these coordinates make this equation true. I'm trying to prove that this point is actually on this line.
Right.
Because that point could be right here. Maybe that's the point that satisfies this equation.
Right.
I'm trying to show any other x and y you choose that satisfies this equation is going to land on this line. That's what remains to be shown.
Oh, okay.
You with me? Okay. So pick an x and y that I know satisfy that equation. I'm going to construct some right triangles here. My coordination is pretty trash. Let's use a blue to draw this down. Notice that that makes a right angle here. And then we're looking at this triangle here with this right angle here. With me so far?
Yes.
Okay. I am trying to argue that this point is on this line.
Right.
The way that I'm going to argue that is I'm going to say that this angle is the same for both this triangle and this triangle.
Right.
You with me?
Yeah, because that's going to show us.
The way I'm going to show that this angle is the same for both of them is I'm going to show that the smaller triangle is similar to the bigger triangle.
Right.
So that's what I need to show. I need to show that this right triangle is similar to the big right triangle. If I've showed that, I'm done.
All you have to do that is show two sides are proportional.
To do that, all I need to do is show two sides are proportional. That's exactly right. So I need to show that this over this is equal to this over this.
Right.
So I need to show this length over this length equals this length over this length. Rise over run for this equals rise over run for this. Okay, what is the rise here? How high is this?
Right.
What is the height of
Negative
this?
CB.
Negative
C
CB.
over B.
That's the height of it. What is this distance right here?
Negative C over A.
Almost.
The height, oh, 0.
What's this distance right here?
Negative CA on the.
If I tell you that the coordinate of this point is -3, what's this distance?
3.
3.
So it's CA.
So it's just CA, it's the negative of its coordinate. This one is just its coordinate. This one is the negative of its coordinate.
That one's not the negative.
No,
Its coordinate.
it's its coordinate, which means that C or B here must be a negative number.
Oh,
Right.
okay. So how is CA?
This distance is always just its positive coordinate.
Right.
Since this is a negative
Oh
coordinate,
yeah, I get what you.
just an accident of how we've drawn the picture. If I had drawn the picture differently so our line was tilting like that, then we would have flipped this one to be positive CB, and this one would have been positive CA, and it would have changed our picture.
If CA was on that side, it'd be positive CA. Right.
Right. Which would flip our picture like this.
Yeah.
So flipping the picture is just going to move your signs around, but it's not going to change out any of the algebra.
Okay.
So, anyways, this is over C over A. And I am trying to prove that this is equal to, this distance over this distance.
Right.
What is this distance?
We don't know yet.
Yeah, we do.
It's X.
No.
Y.
Oh, it's Y.
It's Y. That's what the Y coordinate is.
Right.
What is this distance?
It's X.
No, this is X.
It's CA.
X is your distance this way from the origin.
It's
yeah.
CA plus X.
It's X plus CA or CA plus X.
Yeah.
I'm trying to prove that these two are equal.
Right.
If they're equal, then these triangles are similar, and then xy lies on this line.
Proportional.
Then it's proportional. Perfect. Okay, so when you take one fraction and you divide it by another fraction, that is the same thing as multiplying by its reciprocal.
Right.
So this left-hand side, this is the same thing as negative c over b
Times A over C.
times a over c, which is equal to, c's cancel out and we're left with negative a over b. So this is equal to negative a over b. Now the question is this equal to negative a over b?
Right.
So let's see that. I have y over, I'm going to get a common denominator down here in the denominator. So I'm going to multiply this x top and bottom by a. So this is going to be ax plus c all over a. So get a common denominator in my denominator.
Right.
So I multiplied x top and bottom by big A.
Right, I got you.
So that's over big A, that's over big A, add them together.
Right.
Good with that algebra? Okay. Now, what do I know about this y? And this x? They satisfy this equation.
Right.
That's what we chose. We chose an x and y that satisfy this equation. So whatever x and y are, they satisfy this equation up here. I'm going to take this equation up here, I'm going to solve for y really quick. You with me?
Yeah.
So taking this equation and solving for y, so first off I get b over y is equal to negative ax minus c.
Right. And then divide both sides by B.
Divide both sides by b, and I get y is equal to negative ax minus c over b. I'm going to write this one more weird way. I'm just going to factor out the negative. I'm going to write it as negative ax plus c over b. You with me?
Yes.
Okay. So that is our y. So y is equal to this thing. So we're left with, this is equal to, put the negative sign out front. It's equal to ax plus c over b, all divided by the denominator of this, ax plus c over a. Now when you divide one fraction by another fraction, you multiply by the reciprocal of the denominator.
Right.
So this is equal to, don't forget our negative sign, negative, this one times the reciprocal of that. So we have negative ax plus c over b times the reciprocal.
A over ax plus c, which equals A over B.
So we're multiplying these together, notice that cross cancels with that, and we're left with negative a over b. And so it holds. And so those triangles are in fact similar. And so the coordinate xy gives us a point on that line.
And
Good?
that point is negative AB. That's our y, right?
That is the proportion. In other words, using language that we haven't established yet, what we just showed is that a line has a constant slope.
Yeah. And that's the proportion of the slope.
We basically use the slope to get another point on the line, is one way you can think about it.
Oh, okay.
Actually, not quite. What we showed is pick another point on the line, and it has the same slope. No, I said it right the first way. Pick another point that satisfies the same slope, and it's a point on the line. That's what we did, but who cares in terms of that? The point is that we chose a random xy that satisfied this equation, and it happened to fall on this line. So that will always be the case. So far what we showed is that any equation like this, as long as you satisfy this condition, has a corresponding line. And so we often call these equations linear equations. They're equations that represent lines. Now we're going to do the converse. The converse is we are going to start out with an arbitrary line and show that it has a corresponding equation.
Right.
So I showed that if you give me the equation, I can give you the line. Now I need to show you that if you give me the line, I can give you the equation. That's the next piece. Following that? Okay. So this time, we're going to start out with, let's move to the left here. Not sure how much algebra I'll need to do. This time we're going to start out with some arbitrary line. We don't know anything about it, except for, well, Now, we need to show that there's an equation for this line. So I got a line here. What do I know about a line?
It goes on forever.
It goes on forever. Every line has at least 2 points. So since this is a line, it has to have 2 points on it.
Right.
And those 2 points have to have coordinates.
Right.
So I'm going to pick 1 point on it, and it has to have coordinates. We're going to call it x1, comma, y1. And pick some other random point, and it has to have coordinates. Call them x2, comma, y2. I need to prove that there's an equation of a line represented here.
Right.
I need to prove that we can find an equation that encapsulates this line. Okay, so that is what we're out to do. So I know that the line goes through those 2 points. Now I need to pick some other arbitrary point here. Probably drew this point up too high. Let me drop down some, and then we'll use this as my third point. x2, comma, y2. So now pick some other point on the line, x, comma, y. And I need to show that we can show some relationship like this, such that this satisfies a relationship. You with me? Okay, similar thinking. Since this point is also on the line, when we construct our right triangles, I know that they're going to be similar.
Right.
Let me move these out of the way. So this was a point x1, y1. This was a point x2, y2. And now we construct our, maybe this with dotted so that we don't get mixed up with the objects we're talking about. Construct these 2 triangles. And I know that these triangles have to be similar triangles because that's a point on the line.
Right.
Trying to show that there's some equation we can construct that this point satisfies. The coordinates of that point satisfy. Okay, now since this is on the line, and then these triangles are similar, since they're similar, we know that these proportionalities hold.
Right.
I know that this distance to this distance is the same as this distance to this distance.
Right.
All right, so what is this distance right here?
It's going to be x1 minus x2, absolute value.
This distance, almost. It's going to be y2 minus y1.
Or y. So this way is y, not with x.
Y is this way. We're going up and down. So this is y2's value. This is y1's value.
Right.
y2 minus y1 gives us a distance in 1 dimension.
Right.
Wait, what's y1's value? Oh, from the origin down.
Yep.
Okay.
So as a concrete example, y2 right here might be 3, y1 here might be -2. So we're saying 3 minus -2. Or in other words, that distance is 5 from that picture.
Yep.
Okay. Now, what is this distance?
It's going to be
That's
x1.
No, that's x.
Oh, sorry, this distance.
That one's x1 plus
That's
x2.
No, that's
Minus
x1 plus x2.
x2 minus x1.
Absolute value.
Same logic from before. Well, since we're keeping the order here, we're going to keep the absolute values out of it to keep it prettier.
Okay.
But it turns out if we did these backwards, then they're just negatives of each other and it would have canceled out in the proportion anyways.
Right.
So x2 minus x1. That's that distance. You with me?
Yes.
Okay. And now this has to be equal to, what's this distance?
That
It
is
is x.
no, that's
X.
y.
It's y plus y1.
Y minus y1.
Yeah.
The distance between 2 numbers, take their difference. What's the difference between 100 and 25? It's 75.
It's not 125.
It's not 125. Okay. Similarly, what's this distance?
x1 minus
X, no.
x.
X.
X minus x1.
X minus x1.
X minus x1.
Yeah.
Okay.
Just throw an absolute value on it. Yes.
Well, it doesn't matter here because even if we got the wrong order here, put a negative sign there, put a negative sign there, they cancel out. Put a negative sign there, put a negative sign there, they cancel out.
Right.
So you could handle the negative cases, and then they would still cancel out, and you'd be left with the same proportionality.
How are they equal to each other?
Because these triangles are similar. That's how we know that they're equal to each other.
Oh, yeah. Okay.
So proportionality.
It's like saying 4 over 4 is equal to 2 over 2. It's what we're about to say.
Now,
What if x1 and y1 are on the in the first quadrant?
doesn't matter. So if that point happened to be a point right there,
It would still
all
be,
our math comes out the exact same.
it's still y minus yx equals x. Okay.
Good? All right. Now, I am going to take this, I'm going to write this side of my equation first. So here's my y minus y1. But I'm going to multiply both sides by x minus x1. So that's going to put that over here. So y minus y1 is equal to this thing. y2 minus y1 over x2 minus x1, all times x minus x1. You with me? Okay. That's a pretty famous equation. This is the equation. This is called, what do they call it? Your 2-point form? If you're given 2 points that a line goes through, this gives you the equation of that line.
Probably.
In other words, let's get concrete with this as we derive this for a second, just so you can see it. If I know that a line goes up here through the point, what does that look like? Like a 3, 4?
Probably.
And let's pick another point down here. What does that look like? Like a negative
A 2.
Negative 1, 4.
minus 1, 4?
5.
Doesn't matter. Okay, here's our 2 points. Here's our x2, here's our y2.
Well, technically it's negative.
Or x1, x2,
It's negative
y1,
one.
negative 4. Thank you. That makes a big difference.
It is.
Then what we're saying is y minus y1, let's see, that's negative 4, so y plus 4, is equal to, this minus this is going to be 8, this minus this is going to be 4, times x minus x1. So it's going to be plus 1. That is the equation of the line that goes through those 2 points.
Right. So I find the distance between those lines.
Well, we'll talk about distance here in a second, but the point is, you've already used this equation before. You've seen that before.
Yes.
Now, let's think about this for a second again. y2 minus y1 over x2 minus x1, let's think about that. y2 minus y1, that's our rise. x2 minus x1, that's our run. Rise over run, we call the slope.
Yeah.
So sometimes we replace this whole messy term with just the letter n. This is just constant, 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 constant.
Right.
So replace it with the new constant n. And so you've also seen this equation. Y minus y1 is equal to m times x minus x1. This is called the point intercept form, or the point slope form of the line. So if you know the slope of a line and a point that it goes through, then you can get the equation of the line. And you've already done that before. You with me?
Yeah. Let's do concrete graphing of that, can we?
Sure.
I've always struggled with when that's their y equals m.
Let's say that the point we choose for x1 and y1 is the point negative 1, negative 4.
Okay.
And let's say I give you a slope of 2.
Okay.
So our line goes through this point and it has a slope of 2.
Right.
So if we go up 2, we go over 1. If we go up 2, we go over 1. If we go up 2, we go over 1. If we go up 2, we go over 1. Da-da-da-da-da.
No,
My picture's a bit messy.
So
And the equation of the line would be y minus y1, so y plus 4, is equal to 2 times x plus 1. And you'll notice it's the exact same equation that we had from before, just simplified,
Right.
because I did the same line. Good?
Yep.
Now, we often like to get this y by itself. So we do y is equal to mx,
Plus b.
mx, distributing the m through, minus mx1 plus y1. Used to that? Or you follow the algebra there?
Yeah.
Now, negative, m's just a constant, x is just a constant, y is just a constant. So I have a constant times a constant plus a constant. The result of all that is a constant. So I'm going to relabel this whole thing b. And so then we get our equation, y is equal to mx plus b. Let's think about what that b is. If I plug in 0 for x, then this term goes away.
Right.
And so I'm left with y equals b.
Right.
So it's b is our y coordinate when x is 0.
Right.
So when x is 0, that's on this line, b is our y coordinate. So this point is a coordinate 0, comma b. Or in other words, b is where we cross our y-axis. It's our y-intercept. This is called the slope-intercept form of an equation.
Like that
With me?
Yeah.
Okay, but we were trying to get in a form like this. So lastly, I'm gonna come take this over here, hijack it, and we're gonna write it out in this form. So I'll move this to the other side. I get negative mx plus y minus b is equal to 0. Notice I've got a constant times x plus a constant, in this case 1, times y, plus a constant equals 0. I took a line, and I came up with the equation in this form that satisfies it. So I showed anytime you give me an equation like this, there's a corresponding line. Similarly, I showed you anytime you give me a line, there's a corresponding equation. We typically like the equation in one of these three forms,
Right.
not in this form. This is called the general form. That's why it's written out this way. You with me?
Yeah.
Now, I know that anytime I have a line like this, its y should be negative c over b. It's y-axis, where it crosses the y-axis. So, where it crosses the y-axis should be negative c. What's my c over here? That's b. You with me? Maybe that's a connection that we don't need to make. You're good with it like that. So that's how you come up with these equations for a line.
Okay.
All these equations you know now that you've used 100 times. Okay, so we proved that. Next definition. If ax plus by plus c equals 0, that equation, if that equation is the equation satisfied by the coordinates xy of all points on line L, we say that ax plus by plus c equals 0 is the equation of L. Okay. Yeah, so now we can start talking about, once you get a line, we can talk about the equation of the line, or once you get an equation, a linear equation, we can talk about its line. That's what definition is saying. Define the line of an equation or the equation of a line, which you're already used to. Okay, now let's talk about calculating distances in the plane. So we already talked about how to calculate distances on one line. How do I calculate the distance between 2 points on a single line? The absolute value of their difference. Right? But we're on a single line, I've got the point right here, negative 3, and I got the point right here, 7. Here's 0. How do I calculate the distance between those 2 points? Absolute value of their difference. The absolute value of negative 3 minus 7. Or the absolute value of 7 minus negative 3. Same thing. In both cases, we get 10. Losing you?
No.
Calculating distances in one dimensions.
Right.
Just take the absolute value of the difference. So if this is some point x1, this is some point x2, its distance is the absolute value of x2 minus x1.
Right, that's on a perfect line.
That is on a line.
Right.
Now we want to talk about it in a plane. So now I've got our xy plane. I give you 2 points. This point right here has coordinate x2, y2. This point right here has coordinates x1, y1. The question is, what is the distance between these 2 points? Or in other words, what is the length of this segment?
The length of the segment.
We're gonna make a right triangle and calculate that part.
Perfect. We're going to use the Pythagorean theorem. So how do we get the distance between these points? We're going to construct this right triangle.
You know the length of the bottom ones because it's gonna be.
What's
x,
this distance?
X minus 2. X2 minus
It's
x1.
x2 minus x1.
minus.
And then y2.
We can do
minus
absolute
y.
value if we don't want to worry about direction here.
And then y2 minus y1.
And this is going to be y2 minus y1. Okay, so then what is this distance right here?
It's gonna be
X2 minus X1
a squared.
Let's call this d for a second, just to help us think. So I know that d squared equals this squared plus this squared.
Right.
So it's equal to the absolute value of x2 minus x1 squared plus the absolute value of y2 minus y1 squared. Now, when you take the absolute value of something and you square it, taking the absolute value does nothing. Because when you square something, it already forces it to be positive. A negative times a negative, a positive times a positive. So these absolute values are doing nothing in this case. Good?
Yeah.
So then what's our distance? Our distance then is equal to the square root of
X squared,
x2 minus x1 squared plus y2 minus y1
which is
squared.
which means it is equivalent.
And so this is called your distance formula. So this is how you can quickly calculate the distance between any 2 points.
Right.
If I give you any 2 points in the plane, you can quickly use this equation to figure out the distance between them.
Okay.
So that means that the square root undoes those two.
That
squares.
means it's,
So that means it's x squared. I mean, it's
No.
x2 minus
That
x1
means
plus
it's-
y2 minus y1.
wait,
Right?
No,
That's
no,
That's
no,
what
no.
your equation's saying, isn't it?
don't you do
Let's
d,
think through that for a
That's
second.
way wrong. I'm just saying, that's.
don't you do d squared?
So let's pretend that this distance came out to 3.
Right.
Okay, so we're talking about the square root of some concrete case where that minus that comes out to 3,
Squared.
and this one came out to 4.
Right.
Now you're asking me, isn't this the same thing as 3 plus 4?
It feels like it is.
Yeah.
What's
because
3
it's
times 3?
squared. 9.
9.
What's 4 times 4?
Oh.
16.
16 plus 9 is?
25.
Square root of 25 is?
5.
So 5 is equal to 7. No, doesn't work.
Yes.
I see what you're saying. Okay, so yeah, then that is the answer.
So this is how you calculate the distance between any 2 points.
So you're
Of
saying
their
the
coordinates
square root does not undo the squares.
Square root undoes the squares over a product, not over a sum.
Okay.
So this is definitely the case. If you have the square root of x squared times y squared,
Right?
then this would be equal to x times y. That is the case.
So what?
Why?
Yeah.
Over
Okay,
a product, not
okay.
over a sum.
Because
product,
the
not
square.
sum. Okay, I got you. So if that was 3 times
So
4.
it'd be d equals
if it
3
was,
plus
if it
4.
was 3 times 4.
No. This is d equals 5.
Right. But if
Why?
instead of you're
You
adding.
just said it was.
No.
No,
That's a product.
That's timesing and that's.
That's a sum.
It's multiplying. it.
Oh.
Okay, very different. 3 squared is 9, 4 squared is 16. 9 plus 16 is 25, squared root of 25 is 5. The distance in this case would be 5.
Okay, so you have to add them
But
into
the
this.
distance in that case would
This
be.
isn't a distance formula. That's a product. That's a completely different formula.
So when you're trying to find distance, it's a.
This
product.
is the formula that you care about.
It's a sum.
It's a sum. Because
That's-
it's coming from the Pythagorean theorem.
And why don't you do d squared right there?
So this came from this. It was this squared is equal to this squared plus this squared. Take the square root of both sides.
And then he took it off by. He took it off the D by
Getting rid
adding
of the square root.
I took the square root of both sides. Yeah. So took the square root of this, took the square root of this.
Right.
Okay.
And then you got D. And
Okay, think we're good there.
then, yeah.
So that's how you get the distance between any 2 points. All right, let's talk about the midpoint on a line. So let's say that I've got a line here. I know 2 points on the line. How do I find their midpoint? Let's say I want to find the point in the exact middle of them. What point is that going to be?
Point in the exact middle. If
Find the distance. Find the distance.
Find the distance
and
of both
divide it in half.
between each other and.
So
Wait.
let's say I found the distance between these, and the distance between them was 4. Divided in half gives me 2. How does that tell me what that point is?
Then you have to.
Well, we have to know that's the midpoint first.
So how do we know it's the midpoint? How do we find the midpoint?
How
So I tell you these coordinates, I tell you these coordinates. I want you to find the exact middle coordinate.
If the distance of that is 5, it's 2.4.
Proportional half of the
Right.
length of that.
Say it again.
So make a right triangle that's proportional to half of the full side.
Well, how do I know where to make the triangle stop? How do I know how long to do it?
Okay. I
Draw,
got you.
hey,
I got you.
make
I
a
got
triangle from midpoint to.
you. No, make a triangle that's full. The entire thing.
All right, so we'll make our full triangle. Follow his idea here.
And then
So
half.
we got our right triangle.
And then the midpoint of the bottom one. Send out. to
What's the midpoint of the bottom one?
It's gonna be easy. It's H because it's a straight line. So if
Well, you
that's-
said the midpoint of the bottom one.
right. So
Where?
if
Right
it's-
here? Where? What coordinate do I stop at to get the midpoint of the bottom one?
So if if its coordinate is at 0, that is the origin.
Here's our origin right here.
Oh,
Here's up. This is the coordinate x1, y1. You said pick the midpoint on this segment. Where's the midpoint?
It's between
All right.
x1 and x2.
Let me
x2
try-
minus x1. Divide that by half. Plot your point.
You're getting close.
X2.
What is the middle of 10 and 2? 6. How'd you get that?
That's 6.
I
You took the distance, divided it in half, and added it to each side.
That's a harder way. Hopefully that's not what you did.
um,
What's the middle of 10 and 2?
6.
6.
How do you get that?
I subtract 2 from each side.
I don't even think that you're
You
thinking that hard.
you divide both of them in half and add them together.
Good.
Yes, sir.
You're seeing it probably not how you're used to doing it. Let me give you another one that you can probably calculate in your head. What's the middle of 100 and 150?
125.
125. How would you come up with that number?
You divide it by 2. You divided the distance by 2. That's what I did.
You did arithmetic in your head really quick there.
Alright.
In the middle of 100 and 150 says 125. There was a question in your mind.
Middle of 100 and 100.
Yeah, 125.
120.
How do we get the average of these? I just accidentally said. You just averaged them. Add together, divide by 2.
Okay.
Oh. Oh.
What's the middle of 10 and 2?
6.
6. 12 over 2. 6.
Right.
What's the middle of 50 and 10?
Uh,
30. Add together, divide by 2.
Yeah.
Okay. What is the middle of this x coordinate and this x coordinate?
It's add them together, divide by 2.
Add them together, divide by 2. So whatever this midpoint is right here,
yeah.
its x coordinate is going to be x1 plus x2 over 2.
And then you construct a parallel line.
And what's its y coordinate going to be? Just y1.
Right.
Because it has the same height as this one.
Then you construct a parallel line that goes
It's not x1
through
minus.
that point.
Why is it x plus? x1 plus x2.
What is the average of 10 and 2?
Oh.
Sorry. What's the middle of 10 and 2? You can't say middle without accidentally saying average.
Because you have to add them together.
Yeah, it's just
It's
the
6.
middle of those
It's
2 points.
10
It's the
plus 2
average of those 2
divided by half.
points.
Can't you do that for the hypotenuse?
Sure.
But where's the point?
But you got to
That's
know
the issue.
which direction to point into.
Right,
So the
okay.
point is, the coordinates of this point here, to make a long story short, is x1 plus x2 over 2. That's the midpoint going that way.
Right.
And y1 plus y2
Over 2.
over 2.
That was hard.
So that was harder than I thought it was going to be. But, so that's what we suspect the midpoint is.
Right.
We need to argue that it is in fact the midpoint. How do we argue that that point is in fact on its line? We could check its proportionality using this triangle.
I got you. Right.
And notice that this over this is going to be the same thing as this over this. The 2's just go out.
Right.
And now, so you can check the proportionality. I guess you'd have to do a little bit more work than that. It doesn't quite come out that easily. But check the proportionality to make sure that's on the line. And now how do we check that it's the midpoint? We need to see if this distance is half this distance.
Right.
So let's check this distance really quick. We know what this distance is. That's right here. Sorry, that's just this equation.
Right. Now.
So
we're gonna do the same
V
thing.
is equal to
We're
this.
gonna go x1.
So now let's calculate
Plus-
this distance.
That's what I'm saying. x1 plus x2 over 2
So
minus x1.
call it d1. d2 is going to be the square root of our second coordinate. In this case, I'm going to call that second coordinate
x1 plus
x1 plus x2 over 2 minus our first coordinate,
x1.
x1 squared,
Right.
plus
y1 plus y2 over 2. Oh, comma y.
minus y2,
Oh, right. Thank you.
or minus y1
y1. Yes.
squared. With me?
Yeah.
Okay, let's work through the algebra on this and see what comes out. So first thing I'm going to do is get a common denominator in each of these terms. So I'm going to multiply this one top and bottom by 2. And I'm going to multiply this one top and bottom by 2. Okay.
So you get 2
So D2 is equal to the square root of
x plus x1 plus x2
x1
over
plus
2
x2 plus, or minus 2x1,
2x over 2
all over 2
Right.
squared.
plus y1 plus y2 over
Minus 2.
minus 2y over 2.
Good. Now, let's simplify. So this is equal to, I have an x1 plus x2 but minus 2x1. So notice that this is going to be equal to,
x1.
how many x1s do I have? I have negative 1 x1s.
Okay. Negative x1
So it's
plus
going to be
x2
equal
over
to
2.
x2 minus x1 over 2 squared plus y2 minus y1 over 2
Squared.
squared. With me so far? Now I'm just going to square the bottom of each of these, not the top.
Right.
So this is equal to the square root of, let's draw it a bit bigger. I'm going to square the denominators, the tops we're still going to leave. So it's going to be x2 minus x1 squared plus y2 minus y1 squared, all over now 4. You with me?
That's not correct math, is it?
Yeah. Square the bottom, so this, we have this squared over 4. Square the bottom, so we have this squared over 4.
Wouldn't it be 8?
Okay.
So I could have had this separated if you want, like this.
Okay.
4,
I just,
4.
yeah, I
Oh,
thought,
yeah.
I didn't understand. I thought you were adding
Okay.
2 twos, and I was like, no.
Okay. So we got, yeah, we weren't just adding the 2's. Okay. So it was like that. Now give them a common denominator.
Right.
Okay, I think you're with me now. Now take the square root of the bottom. When I take the square root of the bottom, it's just going to be 2. So this is equal to the square root of x2 minus x1 squared. I'm sorry, I forgot my plus there.
No squared.
Plus y2 minus y1 squared. Yep, still squared.
Fine.
All over 2. We never squared the tops. We just squared the bottom.
What was the point of squaring?
Squaring the bottom. Now we pulled it out of the square root.
Oh, the bottom at the square root. Okay,
Yeah.
I got you.
And now notice, what is this? That's our distance, d1. That is the distance from this point to this point.
And it's proportional.
So d2 is equal to d1 over 2. d1 is what we call this distance. d2 is what we call this distance. d2 is equal to half of d1.
Right.
So it's the midpoint.
Ooh.
With me?
Yeah.
Okay. Last thing we're going to talk about is the equation of a circle, and then we are done
With the book.
with the book. Yep. So the last thing we need to talk about is the equation of a circle. Let's see if we can think how to come up with the equation of a circle. So,
Like,
to construct a circle, what do we need?
by equation of the circle, you need how to build a circle the size it needs
We're
to
going
be.
to come up with the equation that represents a circle. The same way that this equation represents a line. The same way that I can say to you, let's look at the line, y equals 2x plus 3. And that made perfect sense to you. I want to say, let's look at the circle and write out some equation. And have it make sense to you.
Okay.
Okay.
Okay, so what do we need to define a circle?
Pi.
You
Circumference.
pi the circle.
If I have you construct a circle, you don't need to know what pi is.
The radius.
You're right.
You need the radius
You need the radius, and that's it.
and the point to
And
construct
the
it.
origin. And the
Yeah,
origin.
the origin.
And the origin. Okay. So I'm going to say, give me some origin, any origin you want for my circle.
Right.
And we're going to say that that is at some point over here.
3, 4.
Well, in general, we're just going to call it h and k. But yeah, 3, 4 works fine.
Okay.
Okay.
Now you need to give me some radius.
1.
And then 1, 2, whatever, but it's going to be r. We're going to call r.
Radius. Okay.
Now, what does it mean? Let's do blue for our circle. So now we're constructing a circle, means we're talking about all these points. What do I know about all these blue points?
They are 1 radius away.
They're all
From the
are
origin.
away from the origin.
Right, so if now we pick some random point here on our circle xy.
That's r from the origin.
So here's xy, here is hk. For that point and that point, right?
Right.
Pick some point on the circle. What I know is its distance to here is r. Sorry, that's an R. You with me?
Yeah.
So what do I know? Using our distance formula, I know that this holds when we replace this. So I know that R, we'll do R squared. R squared is equal to,
8x
we'll do H minus X, doesn't matter which way we go, squared,
plus y minus k squared.
X minus H, sorry, plus Y minus K squared.
Right.
And this will be a point, xy, whose distance from hk is r.
Right.
So that's the equation of a circle. This is the equation of a circle.
What's the
You give me any hk and r, that equation will give you a circle centered at the point hk, whose radius is r.
Then you take the radius
How?
and spin it around.
Let's get very concrete now.
If we want to do it.
So let's pick a circle. We'll have it centered at 1, 1, like this.
Okay, 1, 1.
So we'll scribble this circle down here somewhere.
So your H is 1 and your K is 1?
Yeah, we're going to pick our h and k to be 1. So our circle is going to be origin right there, and we'll give it a radius of 1. So we're going to be talking about this circle. You with me?
Yes.
So using this formula, let's come up with that circle. That circle has the equation 1 squared, which is 1, is equal to x minus 1 squared plus y minus 1 squared.
Right.
You with me?
Yes.
Let's pick a point that we know is for sure on this circle.
Wait, so you're saying hk is 1, 1.
H was 1 and k is 1. Yep.
Same. And then-
So the origin of our circle is 1, 1.
And then r.
And
Now-
R is 1.
So r is 1.
Yes.
So we're talking about this circle right here.
Right.
I'm trying to give you intuition for the fact that this equation is the circle. In other words, pick any point on this circle and it satisfies this equation.
Right.
Let's pick points that we know are for sure on the circle. So a point I know for sure is on the circle is up here. This is a point 1, 2. Right?
Right. Absolutely.
You know that for sure how again?
Because we had a radius of 1 and our origin's at 1, 1.
Just like 1, 2, 1.
You good?
0,
Yeah, I got you.
1,
So
0.
this better satisfy this equation or we done messed up.
Right.
Yeah.
Let's check. So I'm plugging that in for x, that for y. So it better be the case that 1 is equal to x, sorry, what were we plugging in for x?
1.
1 minus 1 squared plus 2 minus 1 squared. What's 1 minus 1?
0.
0. 2 minus 1 is?
1.
Squared is?
1.
1 equals 1. It worked.
Okay.
So you can pick any point on here and plug it into this equation and it's going to work. Why? Because it's always going to have its distance r from that point. That's how we came up with the equation.
Okay.
We came up with all the set of points whose distance from the origin, or in this case h comma k,
Is 1.
is 1. So that's the equation of the circle and that's how you come up with it.
Okay.
Now that, and we can continue on studying other geometric objects, but there we go. We got lines and we got lines and we got circles, which are the two most common,
Right. With
and the
that-
equations that represent them.
And you can build anything.
And so yeah, that's the foundations for analytic geometry. So analytic geometry, we're taking the axioms of geometry and we're combining algebra with them. So we're using now all our algebra, all our arithmetic from before.
And trig.
Well, you develop trig on top of algebra.
Trig.
But
What was it called that we learned last time?
last time we were talking about spatial geometry,
What was the other word for it?
or solid geometry.
Solid.
No, it wasn't. Not solid. What's
Solid, that's
so when you were talking to us about
Last week, the name of the chapter,
not last week, but what you
Was-
hyperbolic?
space geometry. Oh, hyperbolic, that's something completely different.
Oh.
Hyperbolic geometry was regular Euclidean geometry, the way we know and love, but we swapped out our parallel postulate.
Right. Parallel is not the straight lines anymore that aren't always equidistant. They just don't intersect. They can like this intersect.
Right, so far, what we've been developing was Euclidean geometry. Now, what we just barely started, let me try this again. Here's one way you can think about it. So we were doing geometry. Over here, you can think about a separate class setting up the axioms of algebra
Right.
onto real numbers. Analytic geometry now is built on top of both of them.
Right.
And it's all built on top of logic.
Exactly. If you want it to be a little bit better than that, we could say set theories here,
And then set theories on top of logic.
and then set theories always on top of logic.
Right.
And that's
And logic.
roughly what the pyramid of dependencies looks like. So analytic geometry, it's its own field, where now we're combining algebra and geometry together. We're starting to take geometric figures and represent them with equations.
Right.
So it's a fun course. This was the first course I ever did with Brother Collier was an analytic geometry course. It was absolutely amazing. That's the course that made me go get a math major.
Just loved it.
Just loved it. Because I was just doing computer science at the time. This is what made me double major in math as well. It was that course. It was amazing.
It's pretty cool.
So super fun course.
What does it dive into? What is analytic?
It's a little, it starts with exactly what we were doing here.
This is analytic drawing.
Oh, this is
Combining algebra and geometry together, representing them this way, and then when you start doing a bunch of geometric proofs from here on out, you start doing them with these equations.
Okay.
Right.
And so you could go through proving a bunch of the geometry that we already know and love, but now using analytic geometry to do it and getting corresponding equations for how you calculate things.
Okay.
And then you're able to go further with it because equations enable you to encapsulate things that were harder to encapsulate before. All right, anyways, that is the end of the book for us. The only new other material we will cover from here on out, we've already pretty much all talked about. I will just give you like a crash course on trig
And unit circle.
Are
with
you
the unit circle.
doing homework for trig?
When we do our trig review, all I will require from you guys is you're going to do a drill filling out the unit circle. So I'm going to require you to memorize the unit circle basically. You're going to come to class, we're going to take a 10-minute test where you fill out the unit circle.
Okay.
That's what we'll be.
Are you
2
gonna
minutes.
give us a
said
practice test like unit circle that we can go and fill out?
I'll give you some unit circles, yes.
How many things on unit circle is it?
How?
And you'll give us an exact perfect thing before we do the test, right?
Yeah, we'll go over it. You'll know how to fill it out. There's 12 points on the unit circle.
What's
So you're going to be
the
writing
best way-
the coordinates of each of the points and the angles of each of the points in degrees and radians.
What's the best way?
memorizing
So you're writing
36.
48 numbers.
What's the best way to
Memorizing
prove
48
God
numbers, it's
exists?
so easy.
Go ahead.
What's the best way to prove God exists?
Oh. So we done with the geometry stuff?
Yes.
Yeah.
Okay, so we'll end it there.
Let's go.